Okay, for nearing the final phase of what we have for the differential equations course, okay, we are looking at numerical methods, and there are three types that we're going to be looking into. And one of these, okay, we have the Euler. Okay, and this is going to be the most primitive and least accurate of the numerical methods in so many capacities. And then we have, moving up the ranks, we have what is referred to as the improved Euler method, which is also referred to as the Hoyne method. And then we have one of the most reliable numerical methods is what is referred to as the Runge-Kutta method. And now, in terms of comparing the numerical methods, we'll take as a sample problem. You have the integral of e to the x squared dx as x goes from 0 to 1. And just looking at what we have in Maple. All right, so we have going from 0 to 1. We have for e to the x squared dx. Okay. And okay, now this is the exact result, and just taking what we have here. So if I were to approximate, let's say, to about 5 decimal places, okay, this is going to be right at 1.4626. Okay, so for the exact, okay, so we have 1.4626. Now, in the case of the numerical methods, okay, we have the Euler approach. Okay, we have what you have in the variable h. Okay, that is going to be a reference to the step size. And now we're going from x equals 0 to x equals 1. And if each step is at 2/10, you're like going from 0 to 0.2 to 0.4 to 0.6 to 0.8 and then 1. And so we'll be looking at 5 steps in this case. Okay, for what we have with numerical methods in Maple, you're going to use a student worksheet, and for the opening statement, okay, we'll have with, and we have in parentheses, we have student, and within the parentheses, we have in brackets numerical analysis. And okay, so after entering, okay, and testing out what we have, okay, with Euler. And for the numerical approach, okay, so you have Euler, and you can say that for what we have for the integral of e to the x squared dx. And if we put this in the language of differential equations, okay, so you have d over dx, and for the function, okay, that's going to be y of x, y the dependent variable, x the independent variable, and we have e to the x squared. And we have just with the information, okay, so you have, okay, so we'll say we have y naught is equal to 0, and we're looking at going out to x is equal to 1, and for the step size at 0.2, so we're going from 0 to 1, and so it's going to take 5 steps. So you have the number of steps, okay, so you want to have it 5, and we'll say that for the number of digits. Okay, we'll put this out to 5 digits. And then upon entering, okay, so you have, in this case, you have 1.3088. Okay, so not exactly so close to what we had with 1.4626. Okay, so we're a little bit off. Okay, but let me just show you a little bit of a progression. Okay, so if I just put this in tabular form, so I'll copy this, and say if I want to form a bit of a chart here, and adding the statements, so we're going to have output is equal to information, enter. So if you notice, okay, we have x at 0, and got the x at 0.2, 0.4, 0.6, 0.8, and 1. Okay, and we have with Maple's numeric solution case, had 1.4626 or 27, and you got Euler's results, and here is the size of the error. Okay, now, and let's say that kind of like in Calculus 1 when we were looking at taking numerical methods in integration, like the smaller the step size, the more accurate the result is going to be. And let's say that if I change the number of steps, say if you had the step size at 0.05, and again, we're going from x equals 0 to 1. You think of like 1 divided by 0.05 is going to be 20. And upon hitting return, and if you notice, okay, we have the result is in closer proximity. And just looking at the tabular approach on this one. So again, we have output is equal to information. And we have this particular layout. Okay, if you notice, okay, we have okay, so you have just for the spread here, so you have up to 0.4, and let's say that if I were to continue, and what you can do is that if you want to expand, so you have tabulating, and we can just go with default, and then we have this particular output laid out. Okay, so if you go down to x at 1, okay, so you have your result in the case of the Euler approach, so you have 1.4208. Okay, so we have with the Euler approach with the step size at 0.2. Okay, so you have 1.3088. And in the case of what we have with the step size at 0.05, where we had 20 steps, so we have 1.4208. All right, so the smaller the step size, the greater the accuracy is going to be in terms of what we have that is solvable by numerical methods. Now, moving up the ranks, okay, we have what is referred to as the improved Euler method, or what is going to be referred to as the Hoyne method. And if we look at how the result is going to be if we have just taking a larger step size and see how it compares with Euler. And what is going to happen here is that for the improved Euler, okay, you're going to have Runge-Kutta, and it got same equation, same initial condition, same destination. Step size, you have it at 0.2. Number of steps is going to be at 5. And we're going to include, the sub method is equal to HUN for Hoyne. And we have for the number of digits, okay, so that is 5. And we have for this particular output, okay, so we have a little bit of an excess. And let's say that, just taking same result here, if I expand the number of steps, and we are substantially closer. Okay, so we have 1.4638. Okay, so we have with the Hoyne method or the improved Euler. So we have an H at 0.2. Okay, we have 1.4807. And then we had with the step size at 0.05. Okay, have 1.4638. Okay, so you're looking at substantially closer to 1.4626. Now, in moving up the ranks, now we have the Runge-Kutta, whereupon we have the step size is going to be at 0.2. And to see how that looks in Maple. Okay, now for what we have with the Runge-Kutta method, now you're going to have the opening statement is going to be Runge-Kutta. You got your equation. And we have, again, y naught is equal to 0, x is equal to 1. And we have the step size, okay, we have at 0.2, so the number of steps will be at 5. Now for the Runge-Kutta, your sub-method is going to be RK4, and we have the number of digits at 5. Okay, so we have 1.4627, And if I were to take what I have with the Runga cutter and just put this in tabular form, so again, have output is equal to information and just adjusting the view. All right, and if you notice, okay, you have Maple's numerical solution, the Runga cutter solution, and look at how minimal the size of the error is going to be. So we have, in the case of the Runga cutter, okay, you have cutting to the chase. Okay, so you have 1.4627.